All right, so now we're continuing on with chemical bonding, atomic bonding, and how elements interact. And so we're still in chapter 2. This is the third video about this. So let's get into it. We had just finished in the previous video talking about ionic bonds. So I'm going to start with a little review. Again, going over the parts of an atom. The nucleus contains the two subatomic particles, the neutron, which has no charge, a neutral charge, and a proton, which is positive. Then we find the electrons circling around in orbits or shells, and the electron has a negative charge. We said that when we looked at the atomic number or the number of protons. And in the ideal world, the number of protons was going to equal the number of electrons. Um, and then we looked at the mass number. Right now, that's not a really important thing, but we said the mass number was protons plus the number of neutrons. So with these two numbers, I can find all three subatomic particles in a normal atom, but that the electron was how we were looking at how they bond and how they react. And we said that the electrons in the outermost shell, which was called the valence shell, making those electrons called the valence electrons, um, they are what determine how the atom reacts, and that we can have two electrons in the innermost shell, and then after that there are eight in the next two, and that's all we're worried about in here. So when we were looking at how they were built up, if I knew the atomic number, and let's say we looked at sodium, the atomic number was 11, so that means that it has 11 protons and 11 electrons to start with. And so if we do the math, the 2 in the first, and then we have another 8 in the second, so that's a total of 10. And so then we can go through and say that now there's only one left, and that one ends up being an electron out here all by itself. And so atoms always want to have their valence shell full. And so this atom either wants to find 7 other electrons, which it doesn't do that, or it wants to get rid of the one, and that's the way it works. So I get rid of this, and once I get rid of this electron, that means that I get rid of this outermost shell, and now my outermost shell is full. But now I've gotten rid of one of these negative particles, so that means I have one more positive particle than negative, so I have a positive overall charge. We call that an ion. Now, for covalent bonds, well, and ions can bind with other ions of a different charge. So if I have positive ions next to negative ions, they will attract like magnets. And so that's an ionic bond. Now, what we're looking at here are called covalent bonds. So if you look at the term, co means to share. Valent is talking about the outermost shell, so it's sharing the electrons, where ions are simply the electron is gone. There's no sharing. So these chemical bonds, like we talk about, are all about the electrons. And so this outermost shell, so let's say I've got an outermost shell that has 7, and I know another one that has 7. We can kind of share an electron so that it makes it to where both are full in a weird way. So these covalent bonds, they're actually a really strong chemical bond, or can be, and it's where the electrons are shared. So if I have one, this is the nucleus here, and we'll say this is the innermost, and then this is the next shell, and then over here I've got, it's going to end up looking like someone wearing some goofy glasses here, but we end up sharing an electron that goes back and forth, right? It's not found on either one of the atoms at any given time. It's kind of shared back and forth. And this causes a pretty strong bond and a pretty stable bond. This is looking at two hydrogens. So if you've ever, if you see something that's an H2, all it's saying is these two atoms are sharing their electrons, and that is a co-sharing valent bond, valent shell. Now, this is another example of it, drawing it out. These are little water molecules again, so I've got these two things of hydrogen molecules, H2, and then I've got water here. Now remember, so if I say water, let's go through it just to make sure we're good. Water has 8 protons, which means that it is an atomic number 8. I'll put 2 in the first shell. That means I have 6 in its valent shell under the periodic table look of it. So that means I have 2 seats available. And hey, we've got 2 electrons right here. So that's where this breaks up and that forms this little molecule we call water, H2O. And it's a covalent bond. They're sharing. Now, when this happens, it can happen in one of 2 ways. Either, this can get very complicated, but we want to keep it fairly straightforward right now. It can happen in one of 2 ways. If the 2 atoms share that electron evenly, so I've got these 2, and I'm not going to draw it all out, but let's say I've got this electron and it's going back and forth, and it is, constantly back and forth, back and forth. And so they're sharing it. And let's say this side keeps it 50% of the time, half the time this side keeps it another 50% of the time. That means that neither side is holding the electron longer, so it does not form a pole. And this is called a nonpolar covalent bond. Now let me tell you, the next one makes it a little easier to see. So if, on the other hand, and let me erase these numbers here. So instead of it sharing evenly, let's say this one on this side holds on to and I want to make it exaggerated, 75%, and it's only found 25% here. Right? So what's going on, and then again, let me erase these little lines and I'll draw it again. So what's happening is, it's going like this. So it's found mainly on this side. And what happens is, because the electron is negative, this side, because it is holding on to the electron more, will form a negative pole. This side, because it is not holding on to it as much, forms a positive pole. One of the ways I kind of explain it is, if I have 2 rooms and it's in the middle of winter, and I've got 2 rooms side by side, and I need to try and warm them, and I have one portable heater, and I take it over in one room and I put it in there for an hour, and then I go to the other room and put it in for 10 minutes, and then switch it back over to the other room for an hour, eventually the one room will become much more warm, much more heated than the other one, because the heater is in the one room more. So if the one side, the one atom, is holding the electron longer, it forms a negative pole. Now, this molecule, this polar covalent bond, can then act kind of like an ion. It can start attracting to other things like little magnets. So one thing I want to bring up here, and I'm just want to tell you, because if you can understand this a little, get a little bit of this, it will help. Nonpolar covalent bonds in general are referred to as fat or lipid soluble compounds. Fat or lipid soluble. Polar covalent bonds are called water soluble molecules. And there's a big difference in how they act. And so water, you will see, is a polar molecule, and we'll talk a little bit about a special thing that's called hydrogen bonds. So if I put something in water that is a polar covalent bond, the water itself, because it's got these little poles where the hydrogens and the oxygen are, all right, the oxygen holds on to the electrons more than the hydrogen, so I have this positive around these little arms reaching out, and the negative down here by the oxygen. So if I put this around this molecule, these positive parts might attract to this, and this negative part might attract to this, and it starts forming, it starts letting the molecule be dissolved. That's why it is called a water-soluble substance. So things that are polar covalent bonds are water-soluble, and things that are not, are nonpolar, are not water soluble. And that's why water and oil don't mix, because water has these little hands, we'll call these positive and negative poles. And because a nonpolar covalent bond doesn't have poles, it has nothing to grab onto. And so that's why it is fat soluble. It is not water soluble. And this is a big deal when we start looking at like how the cell membrane works. And, we talk about fat soluble vitamins, water soluble vitamins, fat soluble steroids, water soluble steroids. And we get into why we need bile. It ends up being all about the difference between nonpolar or how nonpolar covalent bonds can't dissolve in water in our body is mainly water. So if you can you get a little bit of an understanding of that, I'm not saying spend a lot of time on it, but if you can grab that at a base level, it will help when we start looking at some other things. So covalent bonds can form polar and non-polar covalent bonds, and it all depends on whether that molecule shares the electrons evenly. If it shares evenly, it is non-polar. If it shares unevenly, it is called a polar covalent bond. And here's a little, this is, science humor can be really funny. Sometimes it can be really stupid. This might be a little of both, but so a grizzly bear and a polar bear are walking along this lake, and they're talking about who's the baddest in the world. And the polar bear reaches over and pushes the grizzly bear into the water, and he starts swimming, and he's trying to struggle, and he's like, help, help, I don't know how to swim. And the polar bear says, don't stress. Your water won't affect you because you're non-polar. Ha, get it? Sorry. Anyway, I always try to throw those things in there. It might be a little stupid, but a lot of times it'll help you remember. So as we move along, this kind of picture is showing this is again water, this is oxygen, these are the two hydrogens over here. And so there's a slightly positive in because the electrons are found on this side more often, so there's a slightly negative in here. So that's a polar molecule. Now there's a special thing that happens with a polar molecule that is involving hydrogen, and especially one that is with nitrogen or oxygen. And the hydrogen bonds end up forming, or hydrogen poles end up forming hydrogen bonds. Now, first and foremost, understand when we say hydrogen bonds, it's referring to bonds that are formed with hydrogen. Don't overthink this. Hydrogen bonds are all about hydrogen. Hydrogen's a really weird element. It only has one proton and it has one electron. There's no neutron. It's just there in the normal. I don't want to get into isotopes, blah, blah, blah. So if I'm talking about a hydrogen ion, that means that this is gone. So we're just talking about a proton hanging out. So if I have these two hydrogens bound, to an oxygen up here, basically, since the oxygen is stealing the two electrons, these are just little protons hanging out, and they have a very weak positive charge. So I like to compare them to like an ionic bond is where you have two really strong magnets, and boom, they just lock together, and it takes a lot of strength a lot of times to pull them apart, depending on how strong the magnet is. Polar covalent bonds in general they might not be as strong as ionic bonds, but they can form little bonds. Now, the next step down are these hydrogen bonds. So I would look at it like ionic bonds are where we have these big, powerful magnets. Covalent, these polar covalent bonds that can form are like a decent sized magnet. And these are like those stupid little refrigerator magnets that just barely stick on. What they do is they're good if I stick on the refrigerator, But if I try to put anything like the simplest little piece of paper between that magnet and the refrigerator, it just falls off. And it can be pretty frustrating. I think, at least I know for me, I'm assuming that most of you understand what I'm talking about, but that's the way I like to think of it, that these hydrogen bonds, and the thing that's amazing about them is they are strong enough to provide a little bit of framework, but weak enough so that we can separate it easily and put back easily. And this is super important because this is what binds each leg of the DNA. So when we need to go in and make a copy of DNA, which we'll look at in I think chapter 4, when we call that transcription, the body goes in and it pulls these little hydrogen apart, these little hydrogen bonds between the nucleotides in there, and they pull it apart, and we read it, and then they come back together. And it can only do that because the hydrogen bonds are weak enough to be pulled apart, but strong enough to give a little bit of framework. So they're very, very important. This kind of shows whenever you see, now you'll never have to, in this class, you're not going to have to worry about this, but if you're looking at in chemistry and stuff, it will become important. When they talk about it, they usually draw these as dotted lines. And what it's saying is these 5 little water molecules actually are kind of bound together because this oxygen has a very weak bond called a hydrogen bond with the other molecules. And this is how water has its properties. Now, we're not going to get into this, but it's really pretty cool when you get into, how water acts. We'll talk a little bit about it. Definitely talk about it in 211 when we have to talk about surfactant in the lungs. But that's what a hydrogen bond is. At its core right now, just remember, if I'm talking about a hydrogen bond, you better understand it's about hydrogen, right? Shouldn't get confused on that. All right, so those are covalent bonds, and I hope that those make sense. Take care and have a wonderful day.